Great. Welcome back. How is everybody? Good? Good. I know this is a tough part of the semester, a lot of exams, a lot of homework. So I want to thank you for staying strong in the face of adversity. We got an exciting class for you today. Well, not particularly exciting. We're going to be covering gutter and inlet design a little bit more. But, maybe relative to your other classes, it'll be exciting. So cool. A couple quick announcements before we get started. Homework 3 is due Friday. So that is your assignment on ArcGIS, HEC-HMS. So it sounds like several of you have started already. That's good. This assignment can take a little bit long. So if you have any technical problems, let me know as soon as possible. And I will help you work through those, okay? Are there any questions on homework 3 before we get started with today's lecture? Yes? Yeah, so I believe what you're referring to is essentially the drainage network computed from the accumulation, right? So you can essentially approximate what the drainage network will be by setting an accumulation threshold and letting that define the streams. If you want to talk about it in office hours, I can kind of discuss in more detail. Yes. Okay. Yes.
Also, same line of terminology, the drainage network is like the rivers and stuff, the streams that you set up, and then the catchment basin is like the whole watershed.
Yeah, so the terminology is kind of fluid. When I say drainage network, what I mean is kind of the network at which channelized flow occurs. So the drainage network in this context refers to kind of areas of channelized flow, areas of piped flow, so anything where there's kind of concentrated flow occurring. Whereas the catchment area refers to the entire land surface that feeds that drainage network. Okay. Okay, are there any other questions on homework 3 terminology? Any other questions? Okay, and I will be holding office hours today at 5:30 when I can answer any questions on homework 3 that you may have, okay? Great. So let's do a quick recap of what we talked about last time. Last time we started our module of the course focused on design of urban drainage infrastructure. And we started off with some of the stormwater fixtures that you will be most commonly working with as a stormwater engineer. So this is street and highway drainage. And we started our discussion of design of gutters. Okay, and what were we trying to achieve in our design of gutters along roadways? Yes.
Keeping the water off the roadway.
Right. So we were essentially coming up with kind of a formal method for designing our gutters in order to keep the water off of the roadways. And particularly, we wanted to limit what? Does anyone remember the technical term? Oh, yeah, we wanted to limit the spread of the water onto the roadway. Or in other words, we wanted to maintain a specified clear width, which essentially refers to the dry area of the road. And we came up with an equation for doing that, which ended up being what's called Izard's equation. So this is an equation that relates the design spread, which we referred to as T sub W, to the discharge cube. And we talked about how we could design the gutter to limit the spread to design specifications. So I gave an example. This is straight out of the Austin Drainage Criteria Manual. But let's say we have a residential collector road that's 24 feet wide, 12 feet in each lane. And we need to maintain a specified clear width for this road of 12 feet, which means we can have an allowable spread of 6 feet of water surface on either side. Okay, and we showed how we could use Izard's equation, and I gave you an example in class where we used this equation to essentially design the gutter so that this spread was maintained. Okay. We talked about 2 different types of gutters, simple gutters and composite gutters. So simple gutters is what we primarily looked at last time, and this is essentially a gutter shaped like a right triangle, right? So this is kind of the most simple kind of gutter you can get, the most simple to evaluate. We have a design spread of T sub W, a lateral slope of S sub X, and a depth at the curb of D. And then at the end of class, we began discussion of composite gutters. So this is essentially a different type of gutter design that allows for a greater amount of discharge while at the same time providing some level of safety for bicyclists by keeping the steep section of the gutter close to the curb. Okay, so it's similar to a simple gutter, except that in this case you have two different slopes. So you have a steeper slope towards the curb and a shallower slope towards the street. Okay, and at the very end of class, I gave you a series of expressions for the discharge and composite gutters. So this is essentially an extension of Izard's equation that breaks up the flow into those two different sections and adds them together. So for each section, you have a discharge corresponding to that portion of the gutter's geometry. Okay, so remember these equations because we are going to do a quick example showing how we can compute the discharge for a composite gutter. And we're going to kind of at the same time show the utility for why we might use a composite gutter in the first place. Okay, so let's do the following example. And I'm going to start this example for you, and then I'm going to let you finish it. So I want you to determine the total gutter flow for a composite gutter with a design spread of TW equals 8 feet. So we have a design spread of 8 feet. Okay, we have a cross slope. I'll just write S sub X, our cross slope for the shallower portion is 0.025. An outer width W of 2 feet. So this is essentially the width of the steeper sloped portion. With a 2-inch gutter depression. So remember in the drawing, I'll just go back really quick. In the drawing, we refer to this component here as the depression depth. Okay, so that's what I'm referring to here. We have a 2-inch gutter depression. Okay. The longitudinal slope is equal to 0.01. And we have a Manning's roughness of 0.016. Okay, so we want to use these equations that I specified in the previous slide to determine the total gutter flow, the total discharge in the gutter for a design spread of 8 feet with these parameters for the gutter geometry. Okay, so probably the most tricky thing to do here. We have these equations. I'll let you finish writing this down. Okay. So we have these equations here that essentially describe the discharge in each part of the gutter. So really the trickiest part is kind of just figuring out the geometry of this gutter and how it fits into these equations. In particular, for the portion of the flow near to the curb, we need to know this slope here. Okay, so let's go back to our drawing. Oops. Okay, let's go back to our drawing. So how can we determine this slope here from the variables that we do have? We want to know the slope of the section of the curb, so the section of the gutter that's closest to the curb. How can we solve this geometry problem? Do you have an idea?
Well, you have W.
Mhm.
You have that.
This is D1 and this is D2.
Oh, yeah. So
Yeah.
just subtract, D2 from
Yep.
right.
Yeah, exactly right. So we can specify the slope S sub W in terms of D1 and D2. So let's go ahead and do that. We have that the slope nearest to the curb is equal to D1 minus D2 over W. Okay, and what are D1 and D2? So we don't have those variables listed here explicitly, but we can construct them. So first, what about for, let's see here. What about for D2? How can we compute that? How about for D2? How do we compute that? Did you have an idea?
Is D1 minus D2 just A?
No, the A is this this section here. So it's kind of sloped downwards here. So I'll give you a hint. For D2, all we need to do is multiply this slope by this distance, right? This distance from here to here. So we can take S sub X times our design spread TW minus W. Okay, so we can take T sub W minus W times our cross slope S sub X. Okay, what about for D1? Is there a way we can figure out the slope for D1? And actually, your question kind of hinted at it.
Once you have D2, can you just get
No, because this is actually, there's actually another little triangle here. Yeah, but it's very close. So what if we just found the side length of this triangle here and then added A, right? So we can take T sub W times S sub X plus A. So let's do that. Okay, and now we pretty much have an expression for our steeper slope. This is equal to T sub W times S sub X plus A, that's the D1 term here, minus TW minus W times S sub X over W. And as we simplify this, what we get is A over W plus S sub X. Okay, so what I want you to do is I want you to finish this problem. So go back and compute the total gutter flow for this composite gutter using the values here. You have the equations from last time. So these are the discharge equations for the composite gutter. And you have this value for our constant K in US units. Okay, so what I want you to do is to just finish up this problem and compute the gutter flow for each component. So QW, Q sub S, and then add them up together to get the total discharge. Okay, and I will circle back in about 5 or so minutes. 0.89, 2.02. Can you tell me which ones? Okay, so let's write this out. So we have QS is equal to 0.89. What are the units? Cubic feet per second. Very good. And for Q sub W, you said 2.02. Okay, very good. So that is correct. So note in this problem, you did have to do a unit conversion for the depression depth from inches to feet. So just keep that in mind. Meaning that the total discharge is equal to 2.9, I guess that'd be 2.91 CFS. Okay. Great. So this problem actually illustrates an important point. What are each of these discharges? So what is QW? Let's draw this out. So we have that. Okay, we have that our total spread is 8 feet, right? Our total spread is 8 feet. Okay, how much is W? W is this distance right here. W is how many feet? 2 feet, meaning that this distance here is 6 feet. Okay, which portion does QW correspond to? Yeah, QW is this one here. QS is the flow in this portion. Okay, so we have that the flow in this small portion of the gutter that's only 2 feet wide is more than twice as much as the flow in this portion of the gutter that is 6 feet wide. Okay, so you can get a huge increase in discharge by increasing your depth or increasing your lateral slope. So if you have a steeper sloped outer section in your gutter, you can achieve a much greater discharge for a given design spread. And that's why composite gutters are often used. You'll often see them here in Austin as well, especially along, major roads, arterial roads, highways, and that sort of thing. Okay, great. Are there any questions on composite gutters? Any questions on this problem? Any questions on gutters in general? Any questions about gutters? Right, okay, cool. Well, then it is time to move on. Okay, so we covered gutters. Our next subject is going to be kind of the other part of street and highway drainage, which is curb inlet design. Okay, so we've been talking up till now about just the gutters themselves. So those essentially channels at the side of the road that convey water. But there's also, in addition to those gutters, another important part in street and highway drainage, which is the curb inlets themselves. And these curb inlets have to be designed so that they can intercept a specified discharge and limit the amount of discharge that is occurring in the gutter, thereby preventing water from getting on the road. Okay, and then primarily we're going to be interested in understanding how the inlet length and the spacing between inlets affects that discharge in the gutter. Okay, so before I start talking about curb inlet design, let me just show you a couple of different curb inlets. Okay, so here's a couple examples of different types of curb inlets. Probably the most common one that you'll see is that one in the upper right-hand corner, which is called a curb opening inlet. So this is a fairly ubiquitous in urban drainage design. Many of you submitted photos of these for your stormwater photos, which I'm going to get to, I promise. So these are very common. They're usually depressed, which means they'll have kind of that slope feeding into it. So notice how this one has this kind of apron that is feeding into the curb inlet, and that greatly increases the interception capacity. So often you'll find that these curb opening inlets are depressed, but they're used pretty commonly along streets and highways because they are often safe for bicyclists, which is one of our design considerations that we need to think about. Grate inlets, so you can see a grate inlet up on the upper left-hand corner. These you will often see on kind of major highways or freeways. So you'll notice if you drive up on the 183 or the I-35 and you're going up the on-ramp, you'll often see these grate inlets along the side of those ramps. So these are great, no pun intended, because they are directly in the path of flow. And so they can intercept a lot of water potentially, but they also have a couple of different drawbacks. So one, not typically the safest for bicycles. And second, they can often clog. So if a lot of debris accumulates on these grate inlets, the interception capacity greatly decreases, and often you'll get flooding very soon after that. On the bottom left, you will see a combination inlet, and this is essentially just a combination of the grate inlet and curb opening inlet. So you get the best of both worlds and also the worst of both worlds together. And on the bottom right, you have what's called a slotted drain inlet. So You'll probably see these around campus a lot. They're often used in parking lots. So this is often when you don't need to intercept a lot of water, when you're often just collecting water over a large impervious area. So you'll see these, for instance, if you walk down Speedway, there are curb opening inlet, slotted drain inlets kind of along Speedway for intercepting that water and carrying it to a storm drain underneath. Okay. Just very quickly, there's also different kinds of specified grates for curb opening, not for curb opening, for grate inlets. And these are often collected in the HEC 22 manual. So these are just specific types of grates that have their hydraulics analyzed through many, many empirical studies so that they have known depth discharge relationships. This here is the P1784 grate. They get very into their different types of grates in these manuals, curved vein grate, and then you got this nice reticuline grate here, this kind of nice honeycomb pattern. So different types of grate inlets. You can look all of these up in your HEC 22 Urban Drainage Design Manual. Okay, so for the next part of class today, through the remainder of the class, we're going to be talking about curb inlet designs. And specifically, we are going to be looking at how we can design the dimensions of these curb inlets to intercept a required discharge. There are two types of curb inlets. Let me just quickly go through the different types of curb inlets. You have what are called on-grade inlets, and you have what are called sump or sag inlets. Okay, and this essentially refers to how they are placed along the local drainage gradient. Today, we're going to be talking just about on-grade inlets. Let me draw a picture for you to show you what I mean. So first, let's talk about on-grade inlets. Okay, and an on-grade inlet is essentially just what it sounds like. It's a inlet that is just placed along a grade or a hill slope. Okay, so let's say here's the ground surface here. This might be the top of the curb. And you have the curb opening inlet coming up like this. Okay, so let's have a curb opening inlet. It goes into an underground box. Sorry. Here. Okay, and you have kind of an opening. So in here, this is essentially the mouth of the inlet right here. And this is an on-grade inlet. So it's essentially just along a hill slope. When you get rain falling, you'll get essentially a water surface that's moving along like this. And when it encounters the curb opening inlet, you'll get kind of a weir flow into the inlet and it'll go down. And then on the other side of the inlet, you'll start to get a buildup of the water surface again as rainfall starts falling on this grade. Okay, so this is the way the on-grade inlets are supposed to operate. The water surface should be below the top of the inlet. If the water surface is above the inlet, you will get a submerged inlet. Okay, so it will kind of look like this. And generally, if this happens, this is not good. So inlets, both on-grade and sump, are meant to operate as weirs and not as orifices. So if you get an inlet that is submerged where the water surface is above the mouth of the inlet, then it's essentially operating out of specification. So you don't want this to happen. Okay, so those are on-grade inlets. Are there any questions about on-grade inlets? Any questions? Note this is a curb opening inlet here. Okay, you can also have what are called sump or sag inlets. And these are essentially inlets that lie at the bottom of a depression in the local drainage gradient. So let's say you have a slope coming in this way and a slope coming in this way. You have your curb here. And at the bottom of this local depression, you have your curb opening inlet. And here's the top of the curb opening inlet. The mouth of the inlet is right here. Okay, and in this case, you will get flow coming in from both sides. So with the on-grade inlet, you only get flow coming in from one end. But for sump inlets, you will get flow coming in from both ends, and you'll get this kind of weir flow again going into the inlet. Okay, and as before, these can also be submerged. You may have water over the top. And again, this is not desirable. Essentially, when it becomes submerged, your interception capacity, the amount of discharge that's going into the inlet, will decrease rapidly as it moves over the top of the inlet. So you'll get it operating much more efficiently if it's operating as a weir as opposed to an orifice. Okay. Are there any questions on these different types of curb inlet situations? Okay. Cool. So let's go ahead and talk about the design procedure for inlets. I'll give you a quick conceptual overview of what we're trying to do, and then I will move into how we can actually design our inlets to intercept a required amount of discharge. Okay. All right. So let's talk about design of curb inlets. I'm just going to give you a quick conceptual overview of what's going on first. Okay, so let's say we have, actually, we're just going to be talking about on-grade inlets. Okay, so let's say we have a street with a curb. The curb is kind of on grade like this. And we have our curb here. Okay. And let's say we have just a couple of different inlets along this curb. Let's draw an inlet here. I'll just draw it below the surface there. And we have another inlet here. Okay. And along our curb, we have some rainfall coming in. This might be rainfall, or it might be runoff from the surface, either from the roadway surface or from the surface above the curb. So I'll just call this W. And as this rainfall falls into our gutter, it's going to create some water surface. Will come up like this. And it will eventually get discharged into our curb inlet. Kind of the same thing is going to be happening here. Okay, and the flow in this portion we will call Q. So in the curb inlet problem, we're interested in designing two primary parts of the curb inlet system. The first is we want to design the length of the curb inlets themselves, which we'll call L. So we want to design the length such that we can intercept some required amount of discharge. And we also want to design this distance here, which we'll call D. Okay, and this is the distance between the curb inlets. So let me just write this out. This is the length of the inlet, and D is the distance between inlets. Okay. Note that I didn't specify the height of the inlet. Why might that be? You have an idea?
It's not what you're using, like, since it's rolling up to the bottom.
Right. So that's very close. So thinking about what I mentioned on the last couple of slides, why might we not need to design the height explicitly? Yes.
Because it's not supposed to go over.
Right. So it's supposed to operate as a weir and not as an orifice. So if the inlet is getting submerged, then you're already out of specification. So we want to design primarily just the length of the inlet and the distance between them to ensure that they're operating within specifications. Great, very good. Okay, so let's talk about how we can actually do this design process. So we are interested in designing these inlets to intercept a given discharge. We can express kind of our design conditions in terms of what's called the efficiency of the gutter. So we can define a gutter efficiency. And the efficiency is essentially just the ratio of the portion of discharge intercepted to the total discharge in the gutter. Okay, so let's just define these terms. E is the efficiency. QI is the interception capacity. This is essentially the portion of flow that is intercepted. And Q, this is the total gutter flow. So this is the total gutter flow. This may be specified to meet some kind of design storm. Okay. And the efficiency is just the ratio of the amount of flow that can be intercepted to the total flow. We can also define what's called a bypass discharge. And this is essentially the component of flow that isn't intercepted. So we can define this as Q minus QI. And I will just define this. This is the bypass discharge. So if the inlet is not able to intercept all of the flow, some portion of flow will pass by that inlet and move on to the next inlet downstream. And that's what's called bypass discharge. Generally, we want to limit this bypass discharge as much as possible, especially near an intersection. Okay, so let's think about these equations a little bit. Note that we can rearrange these equations to get the following. So if we rearrange, we have that the efficiency is equal to QI over Q. So we can rearrange our equation for the bypass flow to rewrite our efficiency as Q minus the bypass discharge over Q. And if we divide this out, this becomes 1 minus the bypass discharge over the total gutter flow. Okay. Okay, if we rearrange this again, we can get another expression for the bypass discharge. The bypass discharge is just equal to the total gutter flow times quantity 1 minus the efficiency. Okay, so that just comes from rearranging this equation here. Okay, so I'm going to highlight this equation here. And I'm also going to go back and I'm going to highlight this equation here. Okay, so in curb inlet design, there's two primary questions we want to answer. Okay, so there are two primary questions we want to answer. First is essentially how long should the inlet be to capture 100% of the gutter flow? So we want how long should the inlet be? And we'll call this length LT. How long should the inlet be to capture 100% of gutter flow? So to be clear, LT refers to that length. LT refers to the length of the curb inlet needed to capture 100% of the flow. Okay. And the second question we're interested in is for an inlet of length L, what fraction of the total gutter flow does it capture? What fraction of the total flow, we'll call Q, does it capture? So with these two questions, we can essentially answer anything we want to know about on-grade inlets. And how do we find the answer to these questions? Well, essentially what stormwater engineers do is they look it up. So there are a large number of empirical equations that are developed specifically for curb inlets. They are listed in the HEC 22 manual, and these are essentially just based on empirical studies of water depth versus discharge over many, many different types of curb inlets. And from these studies, these empirical studies, we get a couple of equations that we can use to design our curb inlets. Okay, so for question 1, we have that the length of the curb inlet needed to capture 100% of the gutter flow is given by the following equation. We have a constant K sub U over quantity N times S sub X, so that's Manning's roughness times the cross slope, to the 0.6 power times the gutter flow to the 0.42 power times the longitudinal slope to the 0.3 power. And note here that KU is equal to 0.6 in US units, and it is equal to 0.82 for SI units. Okay, so again, this equation essentially just comes from a large number of empirical studies, but this is the equation that you would use, for instance, if you were a stormwater engineer in Austin and you were designing a curb inlet. Okay, for question 2, given a inlet of length L, what fraction of Q does it capture? So we can specify that in terms of our efficiency E. And we have that our efficiency needed to, for an inlet of length L is equal to 1 minus quantity 1 minus L over LT, all to the 1.8th power. Okay, so again, these are empirical equations. There's really not necessarily a rhyme or reason for why they appear the way they do, but these are the equations that you will use in practice as a stormwater engineer for designing curb inlets. Okay, are there any questions before I move on? Yes.
That's 0.8 or 1.8 power.
This is 1.8. This is 1.8. And yes, KU is there. Yes. This N is the, let me just write this out. So this N is the Manning's roughness. So this is similar to the gutter equation we used before. SX is the cross slope. Okay. Any other questions on these two equations? Okay, so let's go ahead and apply these to an example problem. Oh, yes. So for curb inlets, instead of having simple and composite, they will be called either just normal curb inlets, or they'll be called depressed inlets. So there'll be another equation for depressed inlets, which is essentially kind of the analogous situation to having a composite gutter. And those equations will be in the notes. I don't know if I'll have time to cover it, but it's very similar. Yeah, it's very similar. Okay. Any other questions on curb inlets, on-grade curb inlets? Okay, cool. Well, let's go ahead and do a quick example, just so you can apply these concepts. Okay, so we have let's say we have a inlet with length L equal to 5 feet. And we want an efficiency of 95%. So that would be E is equal to 0.95. Okay, and let's say we have a longitudinal slope of 0.01, a cross slope of 0.05, a Manning's roughness of N is equal to 0.013. Okay, so our question is, for what discharge in the gutter, Q, can the desired efficiency be achieved? Okay, so I want you to think about those two equations I gave you previously and figure out for what discharge Q can a efficiency of 95% be achieved for this inlet. And I'll give you about 5 or 10 minutes to work on that. Okay. And I will come around and answer any questions you have. All right. Does anyone have an answer to volunteer? Anyone want to volunteer an answer? Yes. 0.19. Anyone else get 0.19? Very good. Very good. So what did you do to solve this problem?
I solved for L using the efficiency that we wanted.
Mhm.
Knowing that LCI is solved.
Exactly. So the idea here was essentially to combine the two equations. And with that, we can compute the discharge needed to meet the desired efficiency. Okay, so if we can write that out as follows. If we just combine the two equations together, we have that our efficiency E is equal to 1 minus quantity 1 minus L, and then we can use our expression for LT, which is KU divided by N times the cross slope to the 0.6 power times Q to the 0.42 power times the longitudinal slope to the 0.3 power, all to the 1.8 power. And if you evaluate this and do a bunch of algebra, what you end up with is Q is equal to 0.19 cubic feet per second. So very good. If you got it, give yourself a pat on the back. Way to go. Okay. And if you didn't get it, also give yourself a pat on the back. Way to go for sticking with it. Okay. Okay. So there were two components of curb inlet design. If we go back to our drawing of the curb inlet design problem, there were two different components that we were interested in. And we talked a bit about the first one. Okay, so if we have some curb inlets, we have rainfall falling on the street and falling on the area upstream of the curb. We wanted to design two different things. The first was the length of the inlet itself, what was the other part that we wanted to design? The distance between the inlets, exactly. So when you're doing curb inlet design, it's important not only to design the inlets themselves, but also design how they work together for a real world gutter curb inlet system. Okay, so the next part we're going to look at is this part here, the design of the distance between curb inlets. Okay, and in particular, we're going to design them such that we are maintaining the desired efficiency and reducing the bypass discharge for each of our curb inlets. So we're going to do this through another example, and this will be essentially the last thing that I talk about today. Let's take an example of a curb inlet system consisting of several different curb inlets together. Okay, so let's say we have a roadway. Okay, it's a little bit sloped. I'm just going to draw the inlets on top. So we have a roadway with several different inlets. You can think of these as just continuing indefinitely down the roadway. Okay, we have some rainfall falling on the roadway, and let's assume that the discharge in the gutter is due only to the rainfall falling on the roadway. Okay, so we're going to assume discharge in the gutter is due only to rainfall falling directly on the roadway. I'll just say on the road surface. Okay, and we want an efficiency of 95%. Okay, and we're going to use the discharge computed from the last example. So we're going to use Q in the gutter of 0.19 cubic feet per second. Okay, so let's just conceptually look at this problem. We have some rainfall, we'll call it W, and let's say W is equal to 1 inch per hour. And that is falling on a road surface. So let me go ahead and draw the road surface here. And our road surface, we're only getting discharge from 1/2 of the roadway. So here's just a drawing of the roadway here. And we have curb inlets here and here. Okay. And let's say that the width of 1/2 of the roadway is B is equal to 12 feet. So this is a residential collector. Okay. So we have some inlets. We've designed them such that they have a discharge of 0.19 cubic feet per second. And what we're interested in is we want to find the distance D. We want to find the distance between the curb inlets that achieves the desired efficiency of 0.95. So we want to find the distance D that achieves the desired efficiency. In other words, we want 95% of the discharge in the gutter to be intercepted by each curb inlet. Or in other words, we want no more than 5% bypass discharge. Do you have a question?
explain the visual, like,
So this is an overhead view of the roadway. We're just looking at one side of the roadway. So we're looking at this left half here. We have rainfall at a rate W that's falling on this half of the roadway. So right here. Yeah, those are lane markers. I wanted to make it clear that this was a roadway here. And then these are your curb inlets. Okay, so we want to design the distance between curb inlets such that we don't get more than 5% bypass discharge for each inlet. Okay, so how can we go about this problem? Where do we start? So first of all, how much discharge is being received by each curb inlet, and where is it coming from? Mhm.
Is it 0.9 cubic feet per second?
So that is the total discharge. So we can write that out. So the total discharge in the curb is 0.19 CFS. So where is that discharge coming from? The roadway. So the discharge is coming from the rain that's falling on this area, right? Is there any other component of that discharge?
from the gutter and the bypass discharge.
Right. So the discharge along the gutter is the sum of the bypass discharge from the inlet upstream added to the amount of discharge that's being created by the rainfall falling just upstream of our curb inlet. Okay, so for each curb inlet, we have that the discharge is a combination of the bypass discharge from upstream, which I'll call QB up. Okay, so this is the bypass from upstream plus what I will call Q sub R. Okay, so this is the discharge from the rainfall directly upstream of the inlet. Okay, and do we have an expression for QR? Can we think of a way to express QR in terms of the rainfall rate? Let's assume the system is at steady state. So we just have a steady state discharge. How can we express QR in terms of the rainfall rate?
W times E times distance.
Exactly. So it'll be W times B, which is the width of the roadway, 1/2 the width of the roadway, times D, which is the distance between curb inlets. Okay, so that's one expression for Q sub R. So let's think about this. Let's think about this component here, QB up. Do we have an expression for the bypass discharge that we can use? You put it in terms of the other variables that we know. Do we have an equation for the bypass discharge? What is that equation? Exactly. So we can express the bypass discharge as the total gutter flow times 1 minus E. Okay, so let's see what happens if we go back and substitute that into our previous equation. So we have Q is equal to QB up plus QR. Okay, let's substitute this in. we get that Q is equal to Q times 1 minus E plus QR. Okay. And let's rearrange this to put QR on the isolated on its own side. So we get QR is equal to Q minus Q times quantity 1 minus E. Okay. And let's factor out the total discharge. We get that QR is equal to Q times quantity 1 minus quantity 1 minus E. Okay. And what does this evaluate to? Yeah, it just evaluates to E. So we get that QR is equal to EQ. Okay, so we have two expressions for QR. Let's go ahead and equate them. So we have QR is equal to the rainfall rate times the road width times the distance between curb inlets. And we have that QR is equal to the efficiency times the total gutter flow. Let's combine those two together. And we have that EQ is equal to B times D times W. Okay. Now what can we do? Yeah, so if you remember back to the problem statement, we were looking for the distance between curb inlets. So now all we need to do is solve for the distance between curb inlets. And that could be expressed as EQ divided by B times W. Let's go ahead and evaluate that. On the top, we have 0.95 times our discharge from the previous problem, 0.19 cubic feet per second. And on the bottom, what was our roadway width again? It was 12 feet. Our rainfall rate was 1 inch per hour. And now we need to do some unit conversions. So we have 1/12 feet per inches and 1/3600 hours per second. And if you evaluate this, what you end up with is a distance of 650 feet between curb inlets. Okay. So this is the procedure, the exact procedure you can use to determine the distance between curb inlets for a given discharge. Okay, are there any questions about this example? Any questions? Any conceptual questions just about curb inlet design in general? Okay, so I have 5 more minutes. What I'm going to do is I'm just going to introduce the idea of a depressed inlet. This was something that you alluded to earlier in class. Most inlets you see in Austin will be of this type. So I just wanted to make you aware of it. Okay, so a depressed inlet, it's essentially, you can think of it as having a composite gutter section that feeds directly into a curb inlet. Okay, so you have our composite gutter section from before. Where now on the left-hand side, instead of a curb, you now have a curb inlet. Okay, so this part is open. The water will be discharging into the curb inlet here. And you may have the top of the curb inlet up here. Okay, and so the definitions you can use are essentially the same in terms of the dimensions. You have that this slope is S sub X. This slope here is S sub W. This distance here is D1. This distance here is D2. with all of the different components being the same as for the composite gutter case. So I'll just very quickly review those dimensions here. And for the length of the inlet needed to capture 100% of flow, it's essentially just an adaptation of the previous equation where we use a different slope now instead of S sub X. Okay, so the length of the gutter needed to capture 100% of flow is KU over N times S sub E. I'll talk about what this S sub E is. So this used to be S sub X, our cross slope. It's now what's called an effective slope, all raised to the 0.6 power times Q to the 0.42 power times the longitudinal slope to the 0.3 power. So this SE, this is essentially replacing the cross slope S sub X, and this is what's called an effective slope. So it's kind of a weighted average of S sub W and S sub X. So S sub E, this is the effective slope, is equal to the cross slope of the shallow portion, S sub X, plus A over W times E naught. So let me just define this. This is the effective slope. This here is the length needed to capture 100% of the flow. And this E naught is essentially a ratio of the flow in the depressed section to the total gutter flow. So E naught is equal to Q sub W over Q, which is equal to Q sub W over Q sub W plus Q sub S. Let me just write these out. Q sub S is the discharge in this portion. Q sub W is the discharge in this portion. Okay. And that is all I have for you today. Please let me know if you have any questions on curb inlets. Today is the last day we'll be covering them. On Thursday, we will be talking about storm sewer design. Okay. So please come to office hours if you have any questions about the homework, and have a nice week.